You had your first quiz on Friday. Hopefully no one had any issues with the quiz, right? It was a very simple quiz. The only thing you really could have done is to, I guess you had enough time to look for the answers in the lecture notes. One of the questions was about the location of the lab, right? Yeah. Okay. So, as I said, pretty simple quizzes, just to make sure that you at least open the lecture notes or lab instructions before going to the lab. And you are going to have your first lab this week, which is the buckling lab. It's going to start today. And next week, we're going to have the heat transfer lab. Do you have any questions? We do have a very small crowd in class, so which is always a welcome thing for me. Yeah. I love to see you guys in class, but a small class is always better. So, I guess to encourage those of you who come to class to keep coming to class, what we're going to do is we are going to have attendance sheets on your output. These are not, again, not mandatory attendances at all. But I'm going to use these. If you come to all of the classes, I'm going to give you 2 lab report reviews. Right? How does that sound? So I guess I need a sheet of paper. Who has an extra sheet of paper? Why don't we do this? Why don't you be the responsible person for the attendance every week? So every Monday, essentially, right? Just give me the sheet at the end of the class, and if you didn't want to come to one of the classes, just send me an email, okay? Let me know you're doing that. So, if you come to all of the classes, you will get 2 lab report reviews. 8 points. Any questions? Okay. Let's talk about the heat transfer lab. The objective of the lab is to study the thermal conductivity of engineering materials, and we are going to find the thermal conductivity and heat transfer coefficient using 2 different experiments. The first experiment is the arm-field linear conduction experiment, which essentially you are going to induce a 1-dimensional heat transfer in a metallic bar that has a sample sandwiching between the 2 metallic bars, essentially. And then you're going to use thermocouples to do the conductivity measurements. We're going to talk about it later. And you're going to move on to forced and free convection analysis. And you're going to measure the heat transfer coefficient for the forced and free convection analysis. Why don't you explain the attendance things to the person who came in right now? And the location of the lab is going to be in the 300 Main Street building, A015. I'm sure you all know where A015 is. And yeah. What is heat transfer? What do we say what do we mean when we say heat transfer? Essentially, to understand this, we need to understand what temperature is. Temperature is the amount of thermal energy in the system. So essentially the bulk of internal energy of each molecule, each component of the system is going to is what we call temperature. Higher energy, higher temperature. That's the idea. And the temperature of the material depends on the source. The sources of energy, you can add more energy to your system through different means. And if you have 2 materials that have 2 different temperatures, you are going to see a transfer of energy between them, which is what we call a heat transfer or heat flow. So the main mechanism behind the heat transfer is the temperature difference between 2 media. If you have the same temperature essentially throughout, so if you have a uniform temperature throughout a material or between 2 materials, there won't be any transfer of energy. I'm guessing you are either in heat transfer right now or you have passed heat transfer, right? So these concepts are a repetition for you. There are different mechanisms through which the heat transfer happens. The first mechanism that we usually learn in the heat transfer class is conduction, which is the heat transfer through a solid or a stationary fluid. Mechanism behind conduction heat transfer is essentially transfer of energy from one atom to another atom through the molecular bonds, essentially, right? So in a solid, you have one atom, higher energy, it will vibrate more, and this more vibration will be transferred to the molecule that is adjacent to it, right? And it will go on like this until all of the molecules have a uniform energy level, okay? And the same thing happens in a fluid. Doesn't have to be a stationary fluid, but the idea is if you have a fluid that is moving, the other modes of heat transfer that are available that are going to be more dominant, like convection or radiation heat transfer are going, not radiation, but the convection is going to be more dominant. So the other mode of heat transfer that is of interest to us is convection, which is essentially heat transfer through the movement of the fluid. Two different types of convection heat transfer. One is diffusion, where a high energy molecule moves to a lower energy area, essentially. Diffuse, high energy molecules diffuse to lower energy areas and stay there, which essentially will make the lower energy area higher energy area. And another mode of convection is called advection, where a bulk of higher energy fluid will replace a bulk of lower energy fluid. So two different types of convection, two different mechanisms for convection, advection and diffusion. But there are also two different types of convection, which are called forced convection and free convection. Forced convection happens when you blow air or any fluid on top of a medium. Right? Then you have, let's say you have a fan set up here, starts blowing, there will be convective heat transfer between this table, this desk, and air. Right? Free convection, on the other hand, happens when there is an energy difference between air and any surface, and that energy difference will cause a density change in air, and that density change will cause a very small motion in the fluid, circular motion. So higher density air moves to lower density areas, and so on and so forth. This is called free convection, forced convection. And we're gonna investigate the difference between the two in their capabilities and their strength of heat removal from a hot surface. The other type of heat transfer that we don't really investigate in this lab is radiation. Radiation is happens through the movement of photons or electromagnetic waves. Doesn't really need a medium to transfer energy. As long as there are two surfaces that have different energies, they can radiate energy from one. We can have energy radiation from one to another medium, and any surface is radiating energy out of it. Any surface that has a temperature higher than 0 degrees Kelvin. So all surfaces at all times are receiving radiation and emitting radiation, right? The radiative heat transfer that we deal with, which uses a sigma epsilon t to the power 4 minus t surrounding to the power 4. That is essentially the net heat transfer. Radiation out minus radiation in, essentially. That's what we do. But we don't really investigate, we don't really talk about, we don't really do any experiments on this type of heat transfer in this lab. Okay. First experiment we do is using the on-field device, linear conduction device, to investigate conduction heat transfer and measure the conductivity of a sample material. How do we do this? Before understanding how we do this, we have to learn about the theory behind linear conduction. We have a law called Fourier's law of heat conduction, using which we can relate the heat rate, the amount of energy that's being transferred between two different walls. Let's say this is the two walls, one wall, the other wall. We can measure the amount of heat, we can relate the amount of energy transfer, Q of x, to the area, the cross-sectional area of these two, and their temperature difference divided by the distance between the two surfaces. So heat rate is related to area multiplied by the temperature difference divided by the distance between the two surfaces. Using the Fourier's, again, using the Fourier's law of heat conduction, we can relate these two. So this relation becomes an equation when you add the conductivity of the material. So the ability of the material to transfer heat. So heat rate, or the amount of energy that is transferred between the two surfaces that have different temperatures, is equals to conductivity of the material multiplied by the cross-sectional area multiplied by the temperature difference between two surfaces divided by the distance between the two surfaces. Okay? Very simple. We're going to take this law and we're going to design it. We are going to design an experiment that is going to let us measure the heat rate, the area, the distance, the temperatures to calculate the conductivity of the material. Okay, let's actually go to, this is our equipment. There are a couple of things that you need to consider when designing this experiment. The first thing is this Fourier's law that we have talked about so far. It's a one-dimensional relationship. So it relates the heat rate to the temperature difference of 2 points essentially on two surfaces, and that heat has to transfer in only one dimension. You can definitely do a three-dimensional, two-dimensional heat transfer as well, but we have to use a different equation for it, which is going to be a little more difficult. Okay, so we have this equation. It has to be a one-dimensional case. What can we do to make sure that this is a one-dimensional heat transfer? You're going to have your heat transfer medium. One side of it has to be exposed to a heating element. The other side has to be exposed to a cooling element. And in between, surrounding it, you have to have perfect insulation. So essentially, you are forcing energy transfer from this point to this point. See, transfer is happening in one dimension. And then we're going to measure the temperature at different locations. Because of the aspect ratio of this rod, we can assume that the temperature, cross-sectional temperature, remains the same at each cross-section. So if we can measure the temperature outside of this rod, inside the insulation, we have the temperature at each cross-section. So we can measure the temperature at different locations. We have made sure it's a 1D heat transfer, and we can also measure the power input because we are adding the power to the system. The power is given to the system by us. It doesn't come from it. If you have a power source, you are adding some power to the system. You just have to turn on the power source and it will start heating up the system. How do we calculate the power? The specific system that we have lets you read the voltage and the current of this power supply. You multiply voltage by the current, you have the electrical power. And also the assumption there is that there is no power loss. We have the power, we have the Q, we have the temperatures. We have made sure it's a 1D heat transfer. The other thing that we have to do is to measure the distance between these thermocouples, right? So distance. And the last thing that we have to measure is the cross-sectional area of the sample. You can actually take this off. You can measure the cross-sectional area of the sample. You have everything you need. You have your Q, you have your area, you have your delta X, you have delta T. We can find the conductivity of the material between each temperature measurement. Okay. So, depending on the type of material and where the thermocouple is located, you're gonna see, let me see. I'm actually drawing this. You're gonna see this type of distribution. Let's say this is we start from here. This is my y-axis, and this axis I have temperature. And I'm gonna rotate this to make it visually more understandable. So first thermocouple is going to give you this reading, higher temperature, closer to the power source. Second thermocouple, this reading. And then so on and so forth. Right? If the sample material is the same as the material, the test setup material, then your temperature change has to be a line, right? And the slope of this line is the conductivity of the material, essentially, right? So using this data, you should be able to measure 1, 2, 3, 4, 5 conductivities. You can also take this temperature and this temperature, measure a sixth conductivity, right? Not just one conductivity. In theory, all of these have to be the same, right? But this is an experimental measurement, which essentially means that there are a lot of losses, there are a lot of assumptions we have made that are not necessarily 100% correct. So there will definitely be a difference between all of these measurements, which means that you have to do a statistical analysis on this and find the confidence interval, find the standard deviation, and the conductivity you give me has to be average conductivity plus or minus your uncertainty, whatever it is. And this is something you have to do for your buckling test as well. Okay, what will happen to this distribution of temperature if the sample material is different from the test setup material? Two different materials. What will happen to this distribution? Do you understand the question? Yes. So since the material was uniform, we got a straight line, right? What will happen to this line if the material is not uniform? Yeah. The slope will change, which essentially means that we are going to have a material in between that has a different conductivity, right? So it will look like this. Like where the sample is, you're going to see a different slope. That's the idea. Okay? Just have to be mindful of this. And when you go to the lab, we have two different materials. One of them is brass, the other one is aluminum. And I think the test of the material is also aluminum, but you have to be very careful. You have to make sure that you check the material, because when you're doing the analysis, you don't want to omit any data. You don't want to say that this is the wrong data. You just want to make sure. You just want to make sure what kind of curve you expect to see. You have to see, right? What kind of line you have to see. Any questions so far? This is one experiment. One thing you have to do though, that I guess I forgot to mention, is you have to wait for the heat transfer to become steady state. When you start adding heat to your system and you start cooling it down, all the thermocouples start getting temperature from the room temperature. And then since you're adding in and also cooling at one point, the temperature are going to rise up little by little, right? This is called the transient heat transfer, right? And Fourier's law of conduction does not apply to transient heat transfer. So you have to wait for the whole system to become a steady state. What does a steady state mean? It means the temperature does not change with time. See, this line is plateauing. So at this point, after like 20 minutes, you should reach a steady state heat conduction, right? This is your temperature thermocouples with respect to time. At time 0, thermocouple is reading this. Thermocouple is closest to the heater, and it goes up. At some point, it will start changing. That's when you have reached your steady state heat transfer. Again, you have to wait for the steady state heat transfer to happen. You have to give it like 20 minutes at least. Any questions? Okay. The second experiment you are going to do in this lab is the heat transfer coefficient calculation for a cooling of a heated copper block. So you have this type of copper blocks. This is connected to a thermocouple. This is connected to your data acquisition device. You just put it in a pot of boiling water. You let it heat up to 80 degrees Celsius, and then you take it out. You have two copper blocks. You put one in front of a fan, and you let one just be exposed to air, right? So one mechanism is forced convection, but the other mechanism is free convection. And then you have to do some analysis to find out the heat transfer coefficient in each case and see which one is going to give you a higher heat transfer convection, heat transfer coefficient. But the theory analysis of this is pretty difficult, right? We have a convection, we have conduction, and it is also a transient case, right? Literally, we want to see how fast or slow your temperature changes over the copper block's temperature changes over time. So to make things simpler, we have come up with this long capacitance method. Long capacitance method assumes the conduction inside the copper block is instant, which means that we are assuming the temperature across the copper block is the same at all time, which essentially means that we are saying that the conduction happens at a much faster time scale compared to the convection with the outside. And we're going to treat the convection outside as a heat source. Those of you who have passed heat transfer course have seen this before and have solved problems with this method, but you don't really need to. If you have not passed the heat transfer course, you don't really need to know the theory behind it. You just have to know how to use the method. Okay, so we are making an assumption here, and the assumption is the conduction inside the copper block happens at a much faster rate compared to the convection outside of the block. What is the result of this assumption? Is this. So we can find the changes of temperature. We can find an equation for the changes of temperature with respect to time. What is the temperature with respect to time? Where is that? This is temperature. This is the temperature that is changing with time. This T infinity is your ambient temperature, your surrounding temperature. Ti is the initial temperature. And then T minus T infinity divided by Ti minus T infinity is equal to the exponential of negative heat transfer coefficient, which is the thing that you want to calculate, multiplied by the area of the block. You just have to, it's actually a cube. You just have to be mindful of the fact that this is the total area of your copper cube. So 6 times the all the squares, right? Divided by the density of the copper that you have to look up from online sources, multiplied by the multiplied by the volume of the copper block, multiplied by the heat capacity, multiplied by time. So essentially, you heat up the copper block to 80 degrees, 90 degrees Celsius. You let it cool down, let's say to 50 degrees Celsius. So you have your final temperature to be 50. You have your initial temperature to be 80. Your surrounding temperature should be around 20-25 degrees. That's the temperature in the lab. You just have to record the amount of time it takes for the copper block to go from 80 to 50 degrees, which will be your time. And everything else can be measured or found from literature, which will leave you with one heat transfer coefficient parameter. We calculated two heat transfer coefficient parameters for the two cases. You have the result. you have your result for the heat transfer coefficient. But as I said, we are making an assumption here. So we have to investigate the validity of that assumption. This is where the Biot number comes into play. So we introduce this dimensionless number, the Biot number, which compares the strength of convection heat transfer compared to the conduction heat transfer. This is how we define it. H multiplied by L divided by the conductivity of the solid. So you have your conductivity of your copper there. You calculate your heat transfer coefficient, and your characteristic length can be calculated by this formula, volume divided by the area of the copper. As long as you find this Biot number to be much smaller than 0.1, you can conclude that the assumption you have made is correct. And then you're done with the experiment and the lab. Do you have any questions? Who has passed the heat transfer or has been in heat transfer? Just one. Who is in heat transfer right now? So think of this experiment as a learning a step for your heat transfer course. We should do this experiment later in the semester. If there is no questions, that's it for today's class. See you all next Monday.